Hello, and and welcome to the stream slash video, depending on the time in which you are watching this. Uh, I'm really excited for today. This is going to be a really cool one, I think. Today we're going to be covering a pretty big topic, I think. And I'll put out there, of course, right now, just if you if you can't hear me or my audio is not working or something, then just send a message in the chat and let me know. But today, we're going to be covering a pretty big topic. We're going to be covering USB and writing drivers, but not only that, we're also going to be like reverse engineering existing stuff, and we're going to be getting into like all the techniques involved there and kind of like how you can actually do that in a kind of logical way, how you can start to break the process down a bit. We're going to do this with a device that's like not too complicated, so that's definitely a bonus. It's going to make life a little bit easier, but it's not trivial. It's not completely trivial. Hey Greg, hey, welcome to the stream. So let's just zip to the code first, and there is no code, of course, right? I haven't written anything yet. I have written some stuff behind the scenes to mess around with this, but we're going to start from a blank slate today. And let's just have a little look at the goal for today. So the goal is to get LED and maybe macros, maybe some other related stuff, control running on Linux. And what I meant to write here is for my keyboard, because I have this this keyboard here, which you should be able to see on screen now. This is it's a GMMK keyboard. It's a mechanical keyboard, and as you can see, it's got some LEDs and stuff built into it. Probably can't see super well the colors and everything, but that's not that important for now. But here, if I press some buttons here, you can see that there is some, you can run through various modes and you can get different things going on, and hopefully the camera's picking up some of that. I'll turn the light off in a bit to really show it. But yeah, so you can see there's a bunch of LEDs on there, and you can kind of control things. You can set the brightness like down or off, and you can kind of configure that. There is also the possibility of like setting up macros and stuff like that on this keyboard, so you can actually go in and set it up so that if you press a certain key combination or something like that, then it does a macro command. So that's kind of useful. And there's a whole bunch of stuff. There's profiles, so you have 3 different profiles that you can use. Now the problem is that all of that stuff, like the really nice configuration and like the complete customization of the LEDs and everything, that only exists on Windows. There is a program that you can get, and maybe let's just quickly take a look at the website here. So this is the GMMK. Our mechanical keyboard for the win. Yeah, I'm a bit of a mechanical keyboard like noob in the fact that I've never built one myself beyond beyond this thing. I built this mechanical keyboard once, which is just like almost like a little macro pad with some arrows on it. But I haven't gone through the full motions of building my own mechanical keyboard. So I just bought this one pre-made. It's about $100. Price was a little bit different when I bought it. It was about a year and a half ago, 2 years. And you can see I've got this what is kind of ridiculously impractical super compact version, which is the one without any arrow keys and without any number pad or anything, kind of like the most minimal keyboard you can get. Not the most minimal, but pretty minimal. And so this one, if you were to take a look here, you'll see that there's a software download. If you go to the software download, well, I would have to say, okay, my model, I've got I'm pretty sure I have the ANSI keyboard. Then you can download some software. And then this software is Windows only, basically. And what that means is that I simply can't on Linux configure the keyboard in the same way. So I don't have access to all these nice features that the Windows users do. And I have, hey Tim, hey, nice to see you. And also, Kogior, nice to see you too. Tim says, that has a similar profile to my An Pro. I don't know what that is, but I'm going to take a look at... Oh, yeah. Oh, that's really nice. And it's also with the Gaterons. I think this is also with the Gaterons. Yeah, so it's quite a similar... I'm wondering how you find it without the arrow keys. Yeah, nice. I haven't looked into the firmware options for this keyboard, but that's something maybe I should do, actually. If I'm looking for true customization, I should look into running a sort of more open firmware. I wonder if that is possible. Well, in any case, on Linux, I simply can't run I can't run this software. And I used to run Mac, so I was in the same boat there. I couldn't do anything there either. So that's really annoying. But since I'm a programmer, and since I'm not afraid to dive in and try some stuff out, and since I think everyone here will probably also enjoy this, what I think is we should try to do some reverse engineering on this. So this is the methodology we're going to follow. We are going to basically run that software in a Windows VM. We're going to install the keyboard driver. Well, I've actually already installed it and everything. It's all running there. It's ready. And then we're going to specifically set the VM up so that it passes through the USB connection. So if you don't do that, and there is a whole bunch of kind of stuff that I'm not going to cover for now, because you kind of have to set up VirtualBox in a certain way, and if you use other virtualization software, you're going to have to do this too. You basically have to like go in and set some install some extras so that it can basically allow more USB possibilities. But what we can do is we can pass through the USB keyboard directly to the virtualization software so that it knows it's this specific keyboard and not just like some generic keyboard. That way the driver will also be able to recognize this keyboard, and then what we can do is we can basically just poke around in the software that's provided in order to do this customization stuff. And what we can do is we can sniff the USB traffic from Linux. Because this is still running on Linux, it's still running in the USB bus of Linux, so we can actually just grab the raw packets of USB as they come down the wire, so to speak. And we'll just capture a bunch of that data. And then what we can do is we can just like analyze it and see what it's made of and see how the keyboard does this. Which might sound really intimidating, and I think it can be. Like it can definitely be a really complex process, but I think what we'll find is that this is way more accessible than you might think it is. So yeah, that's basically going to be the task today. And then of course, like once we have made sense of it, we will at the very least make a start on building a driver, because we're not going to be able to cover the full rundown of the driver today, because there's too much functionality involved, and some of it is more complicated than others. But we're going to basically cover the process of how this works, like how we can actually do this, and how you can write a driver in basically any programming language that you want, because USB drivers are typically written in user space rather than in kernel space, which would restrict our possibilities for how we could do that. But luckily, USB, there's something really awesome that we're going to get into called libUSB, and that's going to make our lives really easy for that. And there is going to be some stuff that we won't be getting into in too much detail. Like for instance, we're not going to open the USB spec today, which is a shame. I would love to do that, and I might do that in like a follow-up episode, but it's just going to be too much to do that. So I'm going to try and give like a high-level overview of USB, how it works, what the architecture is, how it's structured. It's a complicated beast in many ways, but it's not as bad as people actually think it is. So without further ado, let's actually just get started. Hey Stephen, thank you. Well, it seems that my OBS may have lost connection for a second there, so I hope we're not going to lose the stream. All right, so let's go over to just this little diagram that I've made, which is like the smallest, most sort of low fidelity approximation of like what a USB device looks like internally. But I think it should give us some idea of how this works. So USB is a huge thing. It's a huge protocol. It's not just a protocol, it's not just devices, it's everything. It's cables, it's signaling, it's like a whole stack that runs up of like from the lowest levels to the higher levels of how these things work. And USB comes in various versions and flavors and speeds, as you probably know, because USB covers like, you know, devices that you had all the way back in the day, which might have been called USB 1, and then there was USB I'm not exactly sure how the numerics worked on this, because there's USB low speed, there's something called USB full speed, then there's something called USB high speed. Then you have USB 3, which is USB super speed. And then I believe there's even an extension on USB super speed. And then of course there's USB-C, which brings a bunch of additional stuff itself. So yeah, it's pretty complicated. And each one of those adds more levels of complication, although a lot of that complication lies in the hardware and not the software. And so from a software perspective, it's not too bad. You can kind of understand it. So the structure of a USB device, kind of, from a real high level, is that it's something which internally has a bunch of things called interfaces. And interfaces can be a lot, like they sort of provide a high level functionality of the whole device. So if you imagine you have like a webcam, it's a good example of a USB device. You have like a webcam, and then inside that webcam you might also have a microphone, and the webcam might actually offer like different video streaming modes, and so it might actually implement each of those as different interfaces. And each interface can actually be controlled independently. So for example, if you're using a webcam, you don't necessarily have to use its microphone. If you're like in a video call, you can use an external microphone like I am now, and still use the video stream from the camera. And yeah, this is kind of the structure that you end up with. And then sort of inside an interface, although not really, but for the purposes of illustrating it like this, you have something called an endpoint. And interfaces have multiple endpoints. And an endpoint is basically like a place that you can send a message to or from. You can think of endpoints kind of being like a literal like port that you can like plug a wire from one place to another, basically from the device to the computer. You can imagine that there's like, you know, inside the USB cable, there's like small cables that go to these different interfaces, and inside the computer, on the other side, it unpacks those and sends those out to various places. What we're actually doing when we're talking to a USB device is we're communicating with these different endpoints. And you have out endpoints and you have in endpoints. And so obviously, those two things are given from the host perspective, so the computer's perspective. So an out endpoint is somewhere where the computer sends data out from. And an in endpoint is somewhere where the computer can get data from the device. And there are various different kinds of endpoints that have different things. This is really like the USB crash course. You don't have to understand all of this, and we'll probably cover it more as we go through. But don't be too afraid of this. If it piques your interest, absolutely go and just Google USB specification. and you will be able to download from the official standards body. You'll be able to download the USB specification, and you can read it, and it's actually quite approachable. I find the most approachable document, and the one that I've referenced the most, is the USB 2 specification, because it's quite broad. It covers all of the previous stuff, but it doesn't have all of the difficulty of USB 3. And you don't have to read every chapter inside that document. Inside that document, you basically, I think the chapters you need to read are chapter 4 and chapter 9. So that's like the architectural overview, and then like basically USB for a software developer. Those are the kind of 2 chapters you need to read. Everything else is like, this is how a cable is structured, and this is how you do differential signaling and inside the cable. It's all stuff like from the hardware side. Yes, so this is a crash course. Don't worry. If you want to go and get more information, just go and check out the spec. Maybe we'll look at it next time as well. But yeah, it's kind of complicated, but it's not too bad. So we've got a device. A device is made of interfaces, and you communicate with interfaces through endpoints. You'll notice that there is this one endpoint up here, which is called endpoint 0. Every single USB device has to have something called endpoint 0, which is like a general control interface. And if it doesn't have that, it's basically an invalid USB device. I'm sure there are devices out there that don't have it. USB is about the most the most standardized thing that people abuse in every possible dimension. Like, people will take USB and do cursed things with it. If you look at like White Quark's tweet stream and everything, you'll see how cursed USB can be. But yeah, we're only thinking about the good way USB is structured. Right, so I'm just checking in with the chat every now and again. Greg says, are you going to implement a HID driver? No, I'm not going to implement a HID driver, because the operating system already takes care of that. So that is one of the things we're going to see, that like the keyboard functionality itself is going to be one of the interfaces within this thing. And actually, I think the way they do this is they bundle it together in one interface. But the keyboard part, that's going to be handled. And that's the nice thing about USB devices. You can write drivers that only target one single part of the whole device. It's kind of like a lot of devices inside. And that's without even getting into compound devices, which are like devices which have a USB hub built into them and like have multiple actual USB devices attached to them, which have their own interfaces and endpoints and everything. It's it can get pretty insane. But we don't have to implement the HID, which stands for Human Interface Device. We actually only need to implement the kind of control endpoint. Although it's not the control 0 endpoint in this case, because they've decided to do something kind of non-standard, of course. We're going to implement like a higher level control thing. So we're just going to be sending control commands basically to this, which allow us to configure like the LEDs and like the macros and switching profiles and that kind of stuff. So luckily, because I think implementing a HID device would be pretty tricky and probably would need kernel stuff at that point. But yeah, that's the beauty of like USB class devices and everything. Like, all the drivers just exist in the kernel, all the hard stuff, and only the vendor specific stuff, only that stuff you really need to do anything with. Nigel says USB 1 back in 1996, it was like keyboards and mice connections. yeah, indeed. In 1996 was even quite it was even quite an early time for that, right? Because back in those days you'd have like PS2 connectors, and they were way more common. I think in those days you would also see like USB to PS2 or like PS2 to USB, like in that weird transitionary phase in the very late 90s, when it sort of wasn't universal yet. All right, this is the USB device. Okay. how are we going to reverse engineer this? Well, I kind of already mentioned it a bit, but this is kind of like an overview of what we're going to do here. So here's the keyboard in the outside world, and here is Linux, which is inside. So the keyboard is picked up by the USB stack inside Linux, inside the kernel. And additionally, I'm running a special kernel module in Linux, which is you can install on every single distribution and plug in, and it just works, called USB Mon, which is the USB monitor. This is our window into USB. This is like we can watch the packets with USB Mon. So what we're going to do basically is we've connected our keyboard in, it goes into the USB bus. We're then going to run a Windows VM, and inside we're going to run our driver. And so our keyboard is going to get passed through into the sort of Windows USB stack, and the proprietary driver will interact with that, and we'll be able to talk all the way through. But in the meantime, we will be siphoning out USB traffic through USB Mon using Wireshark, which is one of the ways you can interact with USB Mon. Although for various reasons it's not great, but it's possible. And so that's how we're going to get our USB traffic, and we're going to just like dump a bunch of information into there, review it, try and work out what it all means, and then basically, maybe even just play those packets back in. Like, knowing what the functionality is, we can maybe just play those packets back into the system from a Linux driver, and that should work. So yeah, that is the plan. That's what we're going to do. So let's switch over to Windows, and I can show you this software. So Windows, here we are, and I've already got it installed. It's the GMMK keyboard editor. Yeah, Greg, so you say like Wireshark, but for the USB protocol. It's actually, we're going to use Wireshark indeed. but oh yeah, so the device is not detected because at the moment I haven't told Windows, and I haven't told VirtualBox, which is how we're running Windows here. I haven't told it how to pass the USB device through. So I'm not sure if you'll see these menus, probably not. But I'm going into the devices menu, going to USB, and I'm finding the USB device and allowing it to pass through. And I don't know if you picked that up on the mic, but Windows just sort of realized there's a new device. So if we run this again, here we are. So it's picked up the keyboard, and that's really nice. That is us being able to see the software, and this is basically what we're working with here. We're in LED editing mode here, so you can actually go in, and I think you can even like change the color of certain things, or maybe you can't do it in this. Oh wow, that's okay. So in this one, what you can't see, and what I should show here is that as I edit this, the keyboard is also responding, right? So I'm changing colors up here. So this is one of the things that we can capture. But there are a bunch of modes on this thing. So we can actually like go through, and you can see that you get a kind of simulation of like what this is doing. And so there are a whole bunch of these. Apparently it's so you can just see that there are a whole bunch here. There are all different ones, and there are like there are ones where like nothing responds unless you let me share this on the monitor here, so you'll see as I press stuff, Windows is making a sound every time. But yeah, you can see that this is like something where it responds on your key presses. And then there is a custom mode. And so in the custom mode, does not appear to work correctly. So if you look at how the keys are currently shown here. And if I switch to the keyboard view, I don't know if you can see, probably you can't in this light, but this is not actually a reflection of what this window shows in Windows. So that's going to require some that's going to require some help there. Tim, I haven't done anything special with the transition, so I think I just left fade mode on, which just allows. So I turned off just sharp thing and put fade on. Nothing too special. I was thinking about adding some nice ones actually, but so then we can have something like this, and we can also like control the brightness, and do things like that. You can actually also control the speed, so that's another parameter of some of these modes. So if you kind of think about what's going on here, you can already maybe get a sense of what these packets might look like. What kind of data is going to be inside these things? Like, it's going to be like something that is a message that says, hey, I want you to change into this LED mode, like one of these fixed things, because there is literally a fixed list of these things. So there is a certain number, so if I hit this, presumably that will be like number 2 or number 1, depending if it's 0 indexed, and this will be like number 2 or 3, and we'll basically be sending something like that. And then maybe when we do brightness, maybe that's a separate message, maybe that's bundled up into the same message together. There's also this macro thing up here where basically you can add, you can record a macro essentially and then play it back. So that's something we definitely need to take a look at. Yeah, so that's kind of the Windows end. Now we've got an idea. This is what we're dealing with. Now we've seen how USB looks from this high level, and now I want to give you just a quick overview of like what USB looks like when we talk to it from, or when we try to get information from Linux about it. So if I go here into the browser, and I hope this is visible, I'm going to use this command, which is ls. Oh, Windows is yeah, of course I need to like release this from Windows, because Windows has my keyboard right now. So I've taken that off, and then hopefully I've got my yes. So I'm going to run the command ls usb, and I actually have a lot of USB devices plugged into my machine at the moment, because yeah, I've got 2 webcams, I've got a microphone, I've got like a hub with my mouse and keyboard. Yeah, there's a lot of USB things going on. So these are the USB devices I have attached to my machine. Some of them are, well, you can get an idea. Some of them are like built in, like these things down here. They're just like internal hubs. Logitech Stream Cam, so that's my, that is the main camera that you can see up here. I've got an internal Bluetooth device. This is like sometimes, you know, CPU, not CPU, but computer manufacturers, they'll actually, you know, put a it sounds like apparently my video and everything has gotten a little bit out of sync, so that could be yeah, there's not really a whole lot I can do about that right now. I think it's probably because I'm using quite a lot of CPU and stuff, but all right, I'm just gonna have to go through it anyway. So you can see there's a whole bunch of devices here, and the one that we actually want is this one, the backlit gaming keyboard. I don't have any other keyboards in here, so that's a good indication that this is the one we're looking for. And it doesn't label this or anything, but these 2 numbers here are kind of the unique identifier of any given USB device. And so this one here on the left, this is what's called the vendor ID. So this is an ID that is supposed to uniquely identify the manufacturer of this device. Now, in practice, it doesn't always happen, and there are some shared vendor IDs, but I mean, there are kind of enough out there, like, you know, there are like 64K IDs for the USB Foundation, or I'm not actually sure what their actual name is, the USB Working Group or something like that. They distribute these IDs, and I think you can buy them for like $5,000 or something. So this ID is the unique vendor ID, and then this one is the product ID. So this is like kind of the unique identifier for this specific keyboard. So what we can do is we can get deeper information out of USB, LSUSB, and we can do that by saying LSUSB, we want verbose output, and we want it for a certain device. So the device we want is for our backlit gaming keyboard. So if I run this, we get a whole bunch of information out here. And this describes the USB device. So what we can see here is that the manufacturer is apparently Sonix. I guess that's the name. They don't go by the name that they sell these keyboards on the website. The vendor is apparently Microdia. Don't know who they are. It's a different company. It's a backlit gaming keyboard. You can see up here that it uses USB 2. So this is a USB 2 device. And what we're seeing here, right, is we're seeing something called the descriptor. And this is kind of like, this is the way that all USB devices tell the operating system about what they can do. They do it through something called descriptors. So a USB device, when you plug it in, it's required by the operating system that it has to be able to ask for these descriptors. And it does that obviously through the signaling level connection that it does with the device. And then the device has to return this information. And this is all standardized. So if you go and read the USB specification, you will find exactly this breakdown. And it's quite nice, right? You can see that they have names like B length and B descriptor type and BCD USB. And it's got this like, you know, prefix at the beginning, like B. And that kind of tells you something about the data type, which is kind of nice. So this tells you it's a 1 byte field. This is a 1 byte field. This is something called a binary coded decimal field, which confusingly is not actually a binary coded field, but it's a hexadecimal coded field. So inside, we would actually see that there would be 2 hex bytes that describe this, and it would basically, there would be 0200. Actually, I'm not sure if they would be the other way around, like physically you would get like little endy and big endy, and I'm not sure which way it goes in this case, but you would have 2 bytes that basically spit the version number out here. And you've got device class, subclass, protocol. So it gives all this information about what the device is. And then that's the general stuff. So you also get stuff like serial number. And it's not required to provide a bunch of these fields. So a bunch of them will just be 0. Like for instance, you don't have to say that the whole device is of a certain device class, because you can have your individual interfaces say that they are a certain class instead. That's the sort of sub-device aspect of things. So we get max packet size of 64 bytes. That's standard as well. It's like I think that is the maximum for a USB 4-speed device. Could be wrong about that. I'm absolutely not an expert on this, by the way. I just want to put that out there. I'm not a USB expert. There are real USB experts in the world, and I am not one of them. I'm someone who is super interested in it, but recognizes that I don't know that much about it. So then you have configurations, and configurations are like they tell the host computer that the different kind of ways that the USB device can work. So they have to have at least one configuration. Some devices will normally have 2, which is like like almost like you can have a mode where everything is off, and then you can have a mode where everything is on. But for the most part, you'll often see just like one configuration for each device. And then inside the configuration, we get another kind of descriptor that tells us a bit more information. It tells us about like the length of the descriptor and everything. And well, there are different kinds of devices in USB. They actually standardize a whole bunch of like fixed devices, like keyboards, mice, cameras, microphones, payment systems, like, you know, point of sale kind of systems. There's a whole bunch of standardized USB devices, like also MIDI devices and things like that. And in each of those, you know, they have their own special information that comes along with the standard information. So they vary in size, and that's why you get things like this total length. This is going to tell us like how many bytes there are in total, describing all of this stuff. These BM fields, they're bitmap fields. So that's basically, you know, some number. It doesn't have to be a byte. It can actually be longer, but each bit or some of the bits together will form special meaning. So in this case, we're specifically telling the operating system that this is a bus-powered device, i.e. we take power from the bus and it's important for this device to function. And the maximum power that we ask for this device is 400 milliamps, which is it's quite a bit, and it's because, yeah, it's running, you know, all these LEDs. And this is also why I've had problems in the past when I've used this keyboard in a hub in one USB port with a bunch of other devices attached, because, yeah, Apple don't want to put proper USB devices on their computers and make it really difficult. I've had times where if I've plugged too many devices in, like that, not everything stops working, and that's because basically collectively everything is asking for more power than that one USB port can provide. One USB port, if it's just a regular USB port, it can only provide a fixed amount of power, and that varies between the different standards, and it's not that important for now, but there's something to keep in mind. Now we get to the interface descriptor. So what we immediately see here is that this is a human interface device, and it is a keyboard. So that's pretty standard. What that means is that there is going to be a driver in the kernel that deals with this device. Like you don't have to install a custom driver, and that is why I can actually use this keyboard on Linux without having that special Windows driver, because that Windows driver does not provide the actual keyboard functionality. That is the operating system doing that. So we get the HID descriptor, which is another descriptor on top of this. So lots of descriptors in USB, whole bunch of stuff, and a whole bunch of stuff I won't get into here. And what we'll see is that inside there is an endpoint descriptor for this, and it's an in endpoint, and that's an input from the host device perspective. Therefore, like, this is where like keyboard data is coming in. Like, this is the place where the operating system gets keyboard data from. And I mentioned earlier, and I know this is a lot of information, so it's, you know, you're drinking from the fire hose here, and like, trust me, there are places where you could turn the fire hose up and there would be way more water coming out of it. I don't know, this is not an analogy that I want to extend, but there are different kinds of endpoints. So basically USB can communicate in different ways, and it's because there are, you know, devices behave differently. Like, a keyboard supplies a lot less data than, for instance, a camera. A camera has to stream data out like crazy fast as it can. I mean, in the case of this camera, which is quite a high quality camera, it's trying to stream out at either 30 or 60 frames per second, and at, like, you know, HD resolution. So that's a lot of data. It has to just throw that data out. And it's a kind of data where it's both loads of data, but also data where if not all of it arrives. Like if we lose a frame, then it's not important. Like we don't need to resend the frame or anything like that. So there is a certain special they're called transfer types. So they're called transfer types. And in the case of a video camera or a microphone or something like that, they use something called an isochronous transfer type, which is basically like loads of data sent down, but we don't really care if it really arrives or not. We're not going to ask to have it resent. It's just going to get there as quick as possible. There is another type, which is the interrupt type. And so the interrupt type is what the keyboard uses. And it's kind of what you'd imagine, right? You only really care about there being data to send when there is data. So if I press a key, we kind of want to like interrupt the system and say, hey, there's a key here. Like you can go and do something with it. The confusing thing is that if you've ever used microcontrollers or you've ever done like low level programming for operating systems and stuff, then you'll know that interrupts are things that you don't control. They come into the system and you have to deal with them when they happen. That is not the case in USB. In USB, the host computer initiates everything. So the host computer, and in an interrupt, the host computer is basically looking at the device saying, hey, I know you have an interrupt endpoint and you've configured how often you want me to talk to you in this interval. So I'm just going to poll you at a certain interval and I'm going to ask you if you've got new data. And if you have new data, you're going to give it to me. The packet size is 1 byte, so you're going to give me 1 byte at a time. And that's basically it. That's how that will work. And as you can see, there are like, on this keyboard, there are probably less than 256 keys. I actually haven't counted them, but I think it can handle that. I think it can also send more data if it needs. But yeah, so this is how it sends it. It's super simple. There are other kinds, of course, right? There's also something called a bulk endpoint. And in a bulk endpoint, you are sending like either like quite a lot of data, but like again, like a more like, you're not sending it constantly. It's not like you're not streaming video with this. It's more like you have a mass storage device and you're pulling files off the mass storage device. You send each chunk of data to the operating system in like a big bulk package. And in each of these different transfers, USB has some different characteristics that it basically ascribes to these. Like internally, it will allow retries to happen and things like that, and it will do certain validation checks. That's basically the theme. And then there's one final transfer type and also endpoint type, right? They're kind of tied together, transfers and endpoints. The one final endpoint type is control, which is the control transfer. And this is like, it's kind of like the device it's more initiated by the host, but the host is basically doing some aspect of control to the device itself. And in the case of, let's take a video camera, there is a control endpoint that you can talk to, which will allow you to modify things like the brightness and the white balance and the focus and all of those kind of things, turning autofocus on and off. Those are done through control endpoints. And what you might think, if you know all of that information up front, what you might actually think is, does the keyboard use a control transfer endpoint for its configuration of things like LEDs? And the answer is no, it doesn't. What you'll see here is that this particular USB device provides another interface. So there are two interfaces, one keyboard and one apparently mouse. There's apparently a mouse in here. And I think I know why they did this. But yeah, this is kind of a little bit strange. Yeah, I think the reason that it's a mouse is because, and I haven't checked this, but maybe because it has macros, maybe you can do something with the mouse with the macros, and then maybe it wants to actually maybe then it actually wants to like move the mouse manually. I'm not sure, but it actually uses this interface to do the control. And our kind of clue here is that, well, here we get a data in endpoint. This for our keyboard data coming in. In the mouse, we have two endpoints. We have an in and we have an out. And the out, well, that's kind of an interesting one. Why would you have an out endpoint? Because that is where the host is talking to the mouse. And basically, well, we'll need to break some of this down. But this is already a big clue that this is kind of what we end up talking to. So now you have some idea about USB. I hope that it's kind of clear and that there's if anything is not clear, and I see that a couple of people have mentioned that the audio is apparently out of sync with the video. I actually don't think I can do much to fix that now, because if I do something in the streaming software, it's probably going to end the stream on YouTube, and yeah, I think that's I don't know what's going to happen with that, so I'm not going to do it. So what we see here is that this is our vendor ID and our product ID. We're going to use those in the driver, and there's also something called a device number here. So the device number is 35. I think that is not hexadecimal. It's not really clear if it is or it isn't. But the device number here in this case is 35. That's going to be important when we come to capture packets. All right, so let's go back to Windows. Where is Windows? So I think that might be the reason that things went weird here, because Windows seems to have crashed. So let's bring it back up. Hopefully this comes back online and we can try to capture some packets. I'm kind of really on the edge of my I'm really on the edge of what is possible for me to stream on this computer. Like, I've got so many devices. I'm like bumping up against my RAM limitations. So we'll see how this ends up going in the end. I need to set the pass-through up again, which again you can't see, but it's just me clicking something in a drop-down menu. So we got the nice Windows sound again. Run the driver. GMMK. Click yes twice, and we're here back in the thing. So what I'm going to do now is I'm going to take you to Wireshark. So this is Wireshark, and you may know Wireshark from capturing network traffic, because it's a program that's actually meant for that. But it can also, when you have this USB the USB monitor kernel module installed, it can also track USB packets. So that's what we're going to do. I'm going to open up USBmon here, and you're going to see that we're already like grabbing a load of data here. And this is one of the big problems with Wireshark, is there is no way for you to tell Wireshark when it's collecting USB data that you only care about one device. It's an unfortunate thing, because yeah, I'm currently streaming 2 webcams, a microphone, and using a whole bunch of USB devices, and so there's tons of traffic on the USB bus. So the best thing we can do is apply a filter, but it's still going to collect every single piece of USB traffic that comes through, which is super annoying. So what I'm going to do here is I'm going to say that we want to filter, and of course Windows currently has the driver. So I'm probably going to break this all again. Let's see if I can do this without it like completely breaking down. Okay, so I think it's not crashing. That's good. Wireshark. So USB dot device address, and in this case the device address was 35. So I'm going to try and filter that. I'm going to start capturing. I'm going to close the old session. Yes, good. So you can see that we got some traffic in there. These are USB packets that are coming in as we are maybe out of memory kernel kill VM. That is possible. Yeah, I'm not sure. I wasn't quite out of memory yet, and I've given a fixed amount of memory to the VM. So yeah, I kind of thought about budgeting out the memory today a bit. I think it should be alright. I think it's because I messed around with the keyboard driver while it was like speaking to that program. I'm not sure. But in this case, it seems to work. So what we're going to do now is we're going to capture some of this data, and we're going to do it in a bit of a reverse engineering mindset. So let's start capturing again. Go back to Windows. GMMK. Run that. And what I want to do is, yeah, I need to actually pass through again. And run GMMK. Yes. And I'm going to zip back again because what I want is to clean all of this traffic up. So it's, yeah, so it's all clean. So we get it from the beginning. I don't want to see anything that isn't related to the keyboard right now. All right, so the first thing I'm going to do is I'm just going to record a bunch of stuff about the brightness, right? So I'm going to take the brightness. It's currently on its full setting, and this is discrete, right? So there are only like I think four or five individual settings on the brightness. What I'm going to do is I'm going to drag it and I'm going to set it on this one, and then we can go back to Wireshark. And we can see that we dumped out this many packages. And we don't need to know what they are right now. All we need to know really is that it starts here. It's number 96,097. And it runs until 96,256. So what I would actually do here is I would... yeah, I can't use my keyboard at the same time. What I would do is I would come in here and I would say from 1,000. I'm pretty sure Windows just crashed again. It's okay, because I think at this point you've understood the methodology. I would come in here, I would say 96,097. So it's 96,097. Yes. This is the problem. I'm in Wireshark and I've just received this pop-up. I don't know if you can see this pop-up. You probably can't because OBS is strange like this. But it's telling me that it's basically run out of memory to store these packets. And that is, yeah, because I'm streaming video at such a high rate and on two cameras at the same time. So this obviously isn't going to work on stream. I'm not going to be able to show you this. But you've gotten the, you do have the idea now of how this works. So I'm just going to go back to Windows. Am I back? That is the question. So I think I'm back. Yes. It's not. It seems that it wasn't out of memory. It's something to do with crashing. I'm crashing VirtualBox, and then VirtualBox crashing is VirtualBox crashing is actually crashing everything. So it just got logged out. My computer didn't restart, but you know, not that far away. So yes, Greg, as you've mentioned, luckily I have a file. So I've done a bunch of this already. And yeah, luckily we can just open this file that I have already in Wireshark, and we can do the process. So that's what we're going to do now. The Windows portion of this demo. This feels like when you do a demo at work, you know, and just you've got such a good idea of how it should go, and everything just falls apart. So, so that is what's going on at the moment. Let's see. I think I've got all my windows that I need. So if I look here in Wireshark, what you can see is a whole bunch of packets, and these are packets that I captured a couple of days ago when I started playing around with this. I'm actually curious, is the audio and video, are they back in sync now? Because I had to restart OBS, so probably those streams are back in sync as well, I would hope. It doesn't really matter. But yeah, so I've got a bunch of these, and obviously this isn't that much help without knowing what they are. So here in my secret folder, I have the breakdown. So what you can see is that packets 1 to 8, 9 to 16, they are seemingly enabling LED editing mode. These are the notes that I made when I started playing around with this software. So I was turning LED editing mode on and off. So I tried to disable it. I realized it didn't send any USB traffic when I disabled it. I then set the brightness, and you can see I've ordered these now. But I first went from 3 to 2, and then that gave me from 29 till 40. Those packets. So I changed all the brightness settings, and then I set the brightness back, which presumably does the same thing. Then I went through every LED mode that is on the keyboard, and I recorded all the packets from those, and I kind of made a few notes. So I only made this note at this point, but in some of these different LED modes, you have different options available. So in some of them, you can set the speed, for example. In some of them, you can set the direction. In some of them, you can set the color directly. So this is kind of what I noted down. And down here, you can actually go and tell this device, the keyboard, how often it should update. So if you're a gamer and you play a game where the number of key presses that you press per second is like really critical. Like I know that there are some RTS games out there that people play where the actions per minute is like super vital. If that's really important to you, then what you probably want to do is to set your USB report rate really high, because that's basically telling the operating system that it needs to check in with you like 1,000 times a second. Now I think that's slightly overkill, but like currently, I work with this keyboard on the lowest setting, so I work with it at 125 Hertz. 125 times per second, it checks what keys I'm pressing, and for me, that's too many. I don't type that fast, but yeah, you can change this. So this is one of the things I did, and then I experimented with setting the profiles. So this is going to be more than enough for us to actually go in and take a look at what's going on. What I'm going to do now is I'm going to open up a new window, like this one here. I'm going to put it on this side, and I think I'm probably overrunning the... my face is probably in the way, but hopefully not too much. And if it's vital, just tell me in the comments and I'll move it. But let's first take a look at these brightness settings. So let's take a look at what is involved when we go to brightness setting 3. So that's packets 17 to 28. So we go to Wireshark and we scroll down and we find packet 17, and then this is where it starts. So all the way down to here, basically. How do I... Yeah. All of these packets, and can I see if I can zoom this in a bit, because there's no... Yeah. These packets are what is associated with this, like this particular action that happened. So this is probably super intimidating in the beginning. I know it was for me. When I first opened this up, I was like, oh, I'm not sure I have any chance of actually doing this. But what we do is we can see here a lot of information. We can see that this happened at a certain time, like the time from the beginning of when we started this recording, that it's a host to device. So this is the device. We're at 3.15.3. This is like the physical, like on the motherboard with the different USB root hubs and everything. Like it's basically identifying this device in a way that the computer understands, in this dynamic way. So it's a different address. This 15, it was 35 when we just looked at it now, but in this case it's 15. So we had an interrupt out. So the computer sent data from the computer to the device. We can see that here in the direction. The source is the host and the destination is this one. It's USB. They're all USB, so this is kind of useless. And we sent 128 bytes. In here, we can actually look at like what that data is made of. So the frame just doesn't give us that much useful information. That's kind of more on the kernel level stuff. Then we have the USB URB. And I don't remember exactly what the URB acronym stands for. But it's basically what you can think of as what we're seeing here is it's not exactly what's going over the wires. This is what the kernel thinks of as USB. So actually in USB there's a whole bunch of stuff happening. There's like retries and drop packets and things going on, and ACKs and NACKs and like all of this physical layer stuff that you have to do in order to guarantee that data actually goes back and forward. Hey Rodrigo, hey, nice to see you again, man. Thanks for joining. So yeah, there's all this physical layer stuff that happens, but in this case, we're just seeing like the kind of high level view, high level quote unquote, of what the kernel thinks of USB traffic happening. So what we see here is that, let's just make this a bit bigger, that there is a source and a host and everything, and then there's an ID. So there is basically like a transaction ID that's at the top of the packet, and then there is a type, and then there is a transfer type. Like you have to think that all of this is going over one wire. So all that information that we saw related to how we were what we saw in the descriptors basically of the USB, and like, oh, this endpoint and this endpoint is an interrupt and it's an out and everything. All of that information has to be in this packet. So that's kind of what we're seeing. Like, oh, this is going to device 3. It's on this endpoint. So, oh, it's going to device number 3. And this is the direction it's going in. And this is quite a good note to have, in that the endpoints, the most significant bit, signifies whether it's an out or an in endpoint. So there are actually, there are only, the rest of those bits available to describe the actual number of the endpoint. So that's why you saw as well in these descriptors. If I go back to VS Code quickly, and what I will do is I'll run a terminal, and we'll just let's do it like this. Let's take one of these, throw it up here, and then get rid of this one. If I do lsusb vd, I don't remember exactly what yeah, it's this one. So if we look here, we have these different endpoints. So we have endpoint 81, and so that's actually endpoint 1, and the 8 there, that's the most significant bit being set in this. So that's like how we know it's an in endpoint. Then we have endpoint 2. It's also an in, so it also has that top bit set with the 8. And endpoint 3 is an out, so it doesn't have that top bit set. So we actually have endpoint 1, 2, 3 basically marked. So it's quite a straightforward thing to see at that point. Someone says, Yosu Escobar says, could you make a video reverse engineering games? I don't know if I know how to reverse engineer games. I haven't really done much of that. Maybe there is a game that I would like to do that with at some point, but it would probably be more like decompiling at that point and then trying to read what's going on from the assembly and decompiling, getting it back into C code and trying to figure out what was going on. I think it could be interesting to do, but yeah, I'll have a think about it. Okay, so we've got the device number, we've got the bus ID, we've got all of this stuff. And basically, the only thing that's really important for us is actually this leftover capture data, which is the final 64 bytes. This is kind of the actual data associated with this request. So what we see here, and I don't know how well you can see it, but we've got 4, 1, 0, 1, 0, 0, 0, 0, and everything else is 0. So that's the first part of what we send. So already, and we can't make too many assumptions at this point, but already what you could think is like, okay, well, maybe this 04, 01, 00, 00, 01, maybe this is like part of a, like this is describing the type of the thing that we're doing. Like maybe this is saying this is a brightness command or something like that. That was the first thing that I was thinking when I started seeing these packets. Then what we can see is after that, we apparently immediately send, we do something else, right? So you can see that there's more data going on the out. And actually, this is then going from source to, going from the device to the host. And actually, this is information that is like flowing back, but it's not relevant for us. It's kind of like, this is some of the stuff to do with how it's communicating this. So then we, at some moment, initiate another interrupt. And you can see this time, previously we did an interrupt out, and this time we're the host and we are triggering an interrupt in, and we're actually doing it, if you check, we're actually doing it on a different endpoint. We're doing it on the in endpoint. And this is probably, this confused me when I first looked at it, because I wasn't and still am not an expert in USB. And so I thought, this is really strange. Like supposedly we're talking to the device, but we're talking to the device in an in endpoint. And this is when I eventually learned about the whole thing about like, devices, that everything is initiated by the host. So when you talk in an in endpoint to the host, what you're saying is, send me some data. I'm triggering you to send me data. So that's kind of what's happening in this one here. So what we can do is we go down and we get to the data not present. So there's no data associated with this one. So then there's this next host one that goes to the out. And then you can see there's a bunch more data here. Black Bytes says, it's amazing to watch this after I've worked on reverse engineering Logitech's keyboard lighting protocol to apply my own effects, which is basically the same kind of work, just the other way around. What do you mean the other way around? I'm interested to know what you mean. Jace, really interesting, no Twitch. No, I don't stream on Twitch. I stream on YouTube, just mainly because I don't have a good idea about Twitch and everything. I don't have it all set up, so it's YouTube for now. Alright, so then this is us sending a bunch more data to the keyboard. So we're sending basically another burst of information to it. And in this case, what we see is 04 B 006 11 003, and then a whole bunch of zeros. Yeah, this might not be immediately like obvious what's happening here. Like this is at least what I was thinking. Like this is not super straightforward. But the idea is that you actually need to look at a bunch of data in together to get an idea about it. So let's do this. Let's take the first packet of data we sent and we'll copy it. We'll go to VS Code. And what I'm going to do is I'm going to say this is, what's this? Like out 1. We send this. Let's get rid of those first 64 bytes and we'll leave in these ones. So this is where we send 04, 01, 04, 04, 01, 00, 01. Then we have out 2, and this is for, right now this is for brightness level 3. So then the next out packet that goes is this one. Then let's copy these again. Let's drop those in the text editor. Get rid of those first 64 bytes, which is all the other information. And again, now we see this 04, and it looks like these packets start with 04, at least, maybe. We can also see that, excuse me. We can also see that there's a 3 here. Excuse me. And we're setting brightness level 3, so that's also interesting. And what we'll also see is that there is a third packet associated with this. So there is a third out that we send, and you'll notice in the second out we don't send any data. It's just like a sort of, we're getting a very, very low level picture of the USB packets here. Not as low level as the wire itself, but pretty low level. So this actually doesn't have data, but the next one has more data. So let's copy that again. And this is the third part of what we send. And this one is 0402 0002. So at this moment, what we can notice is this is almost like a header and a footer, right? This is like, hey, this is like the start of a transaction and this is the end of a transaction. Like, at least this is what I thought when I first looked at this. I was like, there are 3 distinct pieces of data being sent. This one is just like, you know, it doesn't seem like there's any useful data here. It's just like a little tag, basically. This one seems to have some data in it. And then, well, then that's that. So then let's take a look at brightness level 2 and let's see if we can actually pick something up from that. So if I go to brightness level 2, that's packet 29 till 40. So let's go from here, 29. So this is our first packet. So let's grab that, which is going to do exactly the same thing again, by the way. And we kind of missed something here, which is when we get this, so this is the first packet, this is the second one. When we ask for some data here from the in endpoint, you can see that this time we actually get some data back, right? The first time we make a transaction, like we do the second out packet, it's nothing. Then we ask for some data, and we just seem to get the same stuff back. Like we're asking the device to give us something back, and it basically gives us what we gave it. Then again, we give it this one, this packet, and when we ask for data back, we get the same data back. Finally, in this one, we send this sort of like footer packet, or at least that's how it seems, and we get the same data back again. So that's kind of the pattern we're seeing at the moment. So again, 29, copy the data, and you can already see that that it's the same. This is a header, or at least for the brightness level. Like we're sending the same message at this point. Let's see how it changes when we send a different brightness level. So that's going to be the next packet. So let's just immediately copy this stuff out because it's easier just to analyze it in sort of while it's all together. And for some reason now it's thinking like this is a certain type of thing. Can we just tell it it's plain text? Yeah. So this is out 2 at this point. And what you'll notice here is that it's 04OA 0006 11 01 01 0000 and 2. And so the differences here between the out 2 and the out 2 of this one is it starts with 04, so that's the same. This one's OB, this one is OA. That's a difference of 1, so that's actually quite interesting in and of itself. Then we have 00, then we have 06, 01, 01, all the same. 02, 02, sorry, 00, 00. And then here we have 03, and here we have 02. So I hope you're beginning to see, like, this is, you know, this is where the data is. There is actually data here, and like you can place your bets on what the, you know, what we're going to see in this third out. So let's copy those in, bring them in. Out 3, well, it's just that same footer again. Like, this is literally the footer. So now, if I was to make a prediction on what I think brightness level, so that was brightness level 2, if I was to make a prediction here on what brightness level 1 is going to look like, well, I can actually copy these packets, and let's just see if my prediction's right. I think that this is going to drop down by 1 again, because that's what happened on the previous one. We had, here we had 0B, here we got 0A, so probably this one is going to be 09. And this one, which was previously 02 and the other one was 03, well, this one's probably going to be 01. So let's actually go and look at that packet. So brightness level 1, that's 41 to 52. So we go to Wireshark, 41, we got another header packet, completely the same. This is the one we're interested in. And let's dump that into VS Code and see that, yeah, that is what we got. So we have reverse engineered the, albeit the simplest part, but this is actually the, this is actually now like how we can control the brightness level. And brightness level 0, again, we can just do the same kind of thing, right? And I'm not even going to go into Wireshark. This time I'm just going to, like, you know, confidently, and also I know at this point, but I'm going to confidently say that this is going to go down by 1, so that's going to become 8, and this is just going to become 0. And this is probably what we're going to see for brightness level 0. And at this point we can just get rid of the, you know, the noisy parts. Well, let's just leave it in. But this is it. This is how it works. I see Patrick has mentioned checksum and value. What do you mean checksum and value, Patrick? Right, yeah, I was just catching up with the chat for a second. All right, so at this point we've kind of got enough information just to test some assumptions. So I'm going to open up the index here, which is just a file that I've pre-installed. This may be kind of random, but I really hate that you cannot sniff USB traffic on Mac OS. How has no one worked on that until now? Researched for hours but found nothing. I actually don't know about that. I never did any USB sniffing while I was on Mac. I always had trouble with Wireshark in general on Mac. But I do remember hearing that they have some sort of, I thought that they had something in the kernel that you could, like some sort of kernel module style thing that you could also instantiate and read from, but I don't know, I never looked into it, so I can imagine that Mac is just difficult when it comes to this kind of stuff. Yeah, the one thing that I do want to mention here is that here's the package JSON. I've installed one package aside from TypeScript, and that package is USB. So you can write USB drivers, and I need to go to the web browser, and I don't even have a web browser since it crashed. Give me a minute to fix that in OBS. Yes. Alright, so we should be looking at the browser now. Yep. So there is something called libUSB, And libUSB is a library. Well, it's a library that provides generic access to USB devices. It's intended to be used by developers to facilitate the production of applications that communicate with USB hardware. It's portable, it runs on all the different things, it runs in user mode, and it allows you to work on different versions of USB. So it's just amazing. It's one of the most amazing things out there. Like, it's a user-land library for writing device drivers for USB, and it's just superb. And of course, it's been ported to like every language out there. And Node is no different. Node has bindings for libUSB, and libUSB it's done as a Node extension module. So when you install it, it requires like a pre-built, or it builds on your system like a whole bunch of stuff that runs in Node while it's running, and then the functions that you call from the library, they go through a translation layer, and they end up in like kind of C++ land, where they're talking to Node's APIs, and they can talk to libUSB, and then they can give you the data back in like Node format, and it's kind of this black box exchange thing. And I'm definitely going to cover this stuff one day on the channel, writing Node extensions in C and C++. But yeah, we've got Node USB. And that's what we're going to use today. So I just want to make that clear. You don't have to do anything special. It's just npm install USB. And yeah, I need to remember where we get this from. So I think it's just from USB. And what do we have in here? Yeah, we get these. I think what we can do is just as USB. Might be wrong about that. I'm going to make a main function, which is an async function. Just makes life a little bit easier. Down here we will call our main function, just so it does all of our async stuff. And yeah, what we can do is we can get our device. So the device we're interested in, well, we can do USB dot find by IDs, and we have to provide the VID and the PID, and that is the vendor ID and the product ID. And we spoke about these earlier, and let me just, wow, this is not what I meant to do. Alright, so the vendor ID and the product ID, we've got them up here. This is the vendor ID, this is the product ID. So I'm just going to copy these out, and we'll put them into a constant or something. So const VID, these are hex numbers, so we'll do it like that. And const PID, so that's our product ID, and then we can actually find the device by that. So let's provide the vid and the PID, not the process ID, but the product ID. And well, let's just console log that. Let's see if that's working. Device. So let's see if we just even have that recognized. So I'm going to run tsnode, and I'm going to run source index. And as you can see, we found the device. So here we have it. And you can see we've got some of this information in an kind of, in a less readable format than you get out of LSUSB, but we've got all the information here. You can see that we've got the bus number, the device address. Device address now is 52. I had to plug things out and in, so we've got a different device address now. But we get descriptor stuff, and we get all of this kind of things. And there's more to it than this, right? We can actually talk to the device through its methods. But yeah, this looks about right. So let's keep going. I'm not going to write all the error handling stuff now. You should absolutely write all the error handling stuff. It's just we're relatively short on time, so I won't do it. What we can do now with this device is like we can we need to get hold of its interfaces, basically. just checking in with the chat. Patrick's mentioning expanding on the checksum thing. One field decreases and the other field decreases as well. One field describes the set value and the other describes the value, maybe the checksum of the whole packet, with a very easy checksum calculation. It could be, yeah, I'm actually not sure. It could be. I mean, there's clearly some structure that's like deeper inside. That, you know, of course these, you know, internally this is going to be written in C or C++ or something. There's going to be an actual struct somewhere, structure that describes these things, and like these values are going to be like, you know, there's going to be logical values associated with all these things. So it could well be something like a checksum, indeed. What we need to do is to get the interface, and this is one of the stumbling blocks. So remember, like, there are two interfaces on this thing, and in Wireshark, if we look at any of these transactions, for instance, the ones that we send out, so where did this start? I don't remember where this one started. I think it was probably here on 41. If I expand this information out again, like, we send this to endpoint 3, and endpoint 3 is associated with a particular interface, and the interface is actually interface 1 from a zero index perspective. So what we want to do is we want to get the interface, and we can do that with device dot and then interfaces and then 1. So then we should have an interface. So let's just see if that works. And here this actually tells us interface is a reserved word. Yes, okay, actually that's a TypeScript keyword. So let's call this the, could call it if, but if is also a, let's just call it interf. Oh man, that's horrible. Let's call it device interface. I'd rather take a longer name than have a ridiculous. Okay, so let's check that that works properly. And you can see that it does not. It says cannot read properties of undefined. And this is one of the tricky things that you're going to find working with Node USB. You're going to have to do some Googling around, because what you actually have to do is open the device. So you have to like talk to the device, say that you want to open it. Like, we can look at its descriptor and stuff, but we actually have to open the device, sort of like begin. It's like a file, right? So now let's see if that solves our problem. So I run that, and here we have an interface where we've certainly got a lot more information than we had before. Interface, so we get a whole bunch of stuff. We see this is kind of the original descriptor, it's the device, but then there's a whole bunch more stuff here. So we see also our endpoints, and this is something interesting for us. Like, we need these endpoints. So we need endpoint 3. Let's actually let's give these things names, right? Let's go. Where is the? We don't have LSB open anymore. LSUSB. So the endpoints we're interested in are going to be endpoint 3. This is where we send our commands. So I'm going to call this the const command endpoint. And we also, if we look here in the Wireshark stuff, you can see that we also end up sending stuff to another endpoint, this in endpoint. And the in endpoint that we talk to is the in endpoint is 82, and it's on that same interface, right? So if we look here, above that we have a different endpoint, and it's 82, and that's our in endpoint. So this whole mouse thing still feels sketchy, still feels like kind of not really really true, but yeah, I guess maybe, I don't know. This secondary endpoint, this is where we get information from the device. So I'm just going to call this the interrupt endpoint. It's not really a good name for it, because it obviously is doing a bit more than that, and they're all interrupt endpoints, so it's not that good of a name, but I'll stick with it for now. So what we want to do is we want to get our, and let's get rid of these logs for now because we know that it's working. We want to find these two interfaces. So let's get our control, I'm just going to call it the C endpoint, or control EP. And we can do that by going to devices, and then somewhere in here, I think it's just, is it endpoints, or is it, where do we get these from? Oh, I need to be looking at device interface, not device. That would help. Yeah, in here we have endpoints. So what I want to do here is do find, and that's going to give us an endpoint. And what we want to do is check if that, like, we want to find the endpoint where the address of this endpoint is equal to the command endpoint. That's like these are like meant to be proper constants, so let's do them like that. Control endpoint, and we're going to want to have our interrupt endpoint. iFace. iFace is that is the one I was looking for, yeah. So we should have those two endpoints now. Something worth noting about the USB API for Node is that there is actually Node USB has been around for ages. So Node USB has been here since like almost the very beginning of Node. So it's got this clunky interface that also has a bunch of callbacks and everything involved. So we're probably going to want to like kind of write promise APIs so that we can do async await. But there is a whole second thing, which is that there is actually a standard that's being developed called Web USB. And the Web USB standard is a modern USB standard that's meant to be used by browsers and probably Node and things like that. It's going to be a standard USB interface, which is async from the beginning and which has a whole bunch of like sensible functions, methods, objects, all that different kinds of stuff. And it's actually present in Node USB already, although I've never ever been able to get it to work, and that's on Linux or Mac. I haven't been able to get either of those to work. I'm not quite sure why. Just whenever I use the Web USB APIs, I just don't get any devices back. So right now I'm using the legacy APIs. So what we're doing here is we're getting the endpoints, and then what we need to be able to do is to send data to those endpoints or to request data from those endpoints. And well, the way you do that is that you actually have to like so we've got this endpoint here, right? What we can do with it is we can say do we do it like this? I actually don't remember. Oh, make transfer, that's the API. So what we actually have to do is to make a transfer object out of this. So this is going to be our, this is kind of bad naming because it's now I'm stepping on the wrong names. But we have something kind of a control transfer, which is specifically something in USB, so I shouldn't call it this. I shouldn't call it control transfer. I'm going to call it control transfer for now. Anyway, we can give this a timeout. I'm just going to set the timeout to be 1 second. Like, that's more than enough. Like, if the keyboard is taking more than 1 second to respond to us, then stuff has gone really wrong. And we have to provide this with a callback. So yeah, let's actually make this into a... The tricky thing is, every single time you have to make a request in this API, you actually have to make a new transfer object. So I actually think let's make a class that I'm going to call GMMK, and I'm just going to basically move this stuff into there. So we're going to have an init method where we do this kind of stuff. we're going to obviously have a device. So the type of device is a USB.USB.device. So let's see if we can just find those things. Device from USB/dist USB device. Is that actually exported? No, it's not. Where is this exported from? Oh, it's exported from here. Okay. So that's a device. We don't need, actually we don't need that. We can use a constructor. And here we're going to say this.device equals doing this. And then we're going to want to open the device. Now it's this.device. So yeah, Greg mentions the browser is becoming the OS. I'm not really a fan of that. Yeah, it's a tricky thing actually. You know, it's I'm kind of with you on one part of it. Like, I think that the browser, I mean, if you think about it, it's where you spend probably, aside from programming, it's where you spend most of the time that you're using the computer. And I think things like Web USB are kind of useful in some ways, because it's like that is then it's even easier step for someone to write a driver for your specific device, and if the right security mechanisms are put in place so that you know, browser websites can't all just talk to any device you have on your USB bus, you have to grant access to it, then maybe it's okay. But yeah, I see where you're coming from. Like, it's a bit of a tricky area for sure. Maybe we also want to keep the interface. I think we don't really need the interface once we have the endpoint, so maybe we don't need to do that. And what we can actually do is to have the control endpoint, which is an endpoint. Okay, so that one doesn't exist. This is one of the other things I found about using Node USB, like kind of the types are strewn around all over the place, which is a little bit annoying, but not that bad. So the control endpoint, the interrupt endpoint, my two endpoints that have bad names. In both those cases, we end up doing something like this. Struggling to use my keyboard as normal, as per usual. So we're going to do this. I actually don't know if we'll even need... No, we do need the device because we're going to need to do more things with it. So we're going to get these endpoints. Now we're kind of at the place where we can... What I want to do is I want to make a method now. What I want to do is I want to make a method, and that method is going to be a control transfer method. I need to change this name because this is really bad. Let's call it the command endpoint. Yeah, that's better, because then it's a command transfer. And I want a command transfer to take some data, which we'll provide in node buffer form, because it's just, that's what Node USB works with in the on the under layers, a lot like Bus Pirate in that way. And that's because Bus Pirate, which uses the serial port library, I think serial port is also built on Node USB, so that's the reason that that they share some underlying stuff. So when we do a command transfer, what we're going to do is return a new promise inside where we have our resolve and our reject. And what we're going to do is we're going to make one of these transfer objects. So let's make a transfer. And in this case, it's going to be the command endpoint, make transfer. And you can see that the other thing we need to provide here is a callback. And the callback is in this form. So I'm going to put it out here because actually going to need it in a couple of places. So that takes the error. Wait, what is the argument for this? So it's you know what, in this case that's sorry, I need to this is kind of a by the by thing. It's like a TypeScript thing, so I hate to like do TypeScript specific stuff on this channel because I don't want to give the impression that it's like a bad thing, you know, that it takes extra time. The time is usually worth it, but when you interface with third-party APIs, sometimes you need to work with their types. But the this is going to be like our error callback, and the type of that is like we need to get one of the parameters of this thing. I just want to take out like the type of this second parameter, right? This callback. And the way we can do that is we can use this parameters object in, or this parameters built in from TypeScript. And to that we provide a type. So it's going to be the type of, it's going to be the type of this function. And then we can actually address the second parameter there, and I think that should be, yes, now we don't need to mess around with the callback type. So we can actually create a callback which is going to be the error callback type, which is going to take an error and a buffer. So it's not an error callback, it's the transfer callback. So a possible error, and then any data that we got back in buffer form. That is right? We get data, and is there anything else that comes in there? The actual length. All right, length. So at this point, yeah, I'm glad you like the TypeScript stuff as well, Greg. Yeah, I'm also a fan of it. Like, it can be frustrating when you're just trying to do stuff and then you get stuck having to figure out how to tell the type system something. Like, I can understand people's frustrations there, but I've kind of broken through that point now, and I actually find it really empowering. So when we make this transfer object, we're going to pass it the callback, and the callback inside, we'll just check if we got an error. If we got an error, we will return reject with our error. So we're just turning this whole thing into a promise now. That's all we're doing. Manually, we're manually wrapping it into a promise. And then I guess if we have data, then we will probably return resolve with our data. And the reason we get data and an actual length is because under the hood, the USB library might pass us like a buffer that is larger than the amount of data that we actually asked for, and that can be really confusing. So we will just do data.slice from 0 to length, and that will just make sure that we only ever get the data that we care about. So we're going to make this transfer object, and then we're basically going to, at this point, do transfer.submit. We're going to submit a transfer at this point. So this is where we're going to submit our data buffer. That's the data we're actually sending. And then we're going to get a callback. And this is why I put the callback here, because we can just use the same callback in both cases. Like when we make a transfer thing here, if there's an error at that point, then we're done. But it shouldn't error out. That's the only thing that's used for. And then here, when we actually get data back, that's when that will be used. So cool. All right. So that's how we make a command transfer. We might as well do the same thing here with an interrupt transfer. And in this case, things are a little bit different, because when you do an interrupt transfer, you're not passing data in, you're getting data out. That's kind of the point of it. So what we actually need to do in here is the way this works is that we pass a buffer, and the buffer that we pass gets written into. And the reason that it knows how to do this is because obviously this endpoint, which I need to change here to be the interrupt endpoint. This endpoint is an in endpoint. That is just the nature of this endpoint, and therefore under the hood, Node USB knows that when we pass some data in this time, we're actually passing like the destination buffer here. So we need to make sure that this buffer has enough space in it for the messages that we receive. Luckily, we know how big the messages we receive are. It's also described in the LSUSB thing, so we can go and look that up there. But that's pretty much it. Yeah, we could do some abstraction here on these methods, but I'll leave that for later. So let's actually finally just submit some data to the keyboard. That's kind of what I want to do now. So let's make a device. Let's make a... I'm going to call this a driver, new GMMK. So when we do the constructor, it should boot all of that stuff up. We open the device. And what we can do here is we can say await driver.command transfer, and then let's send some data. And the way we can do this is let's make a let's call this a data buffer. Let's call it a transfer buffer, since we're going to need other buffers to get stuff back. So the transfer buffer, we're going to transfer 64 bytes. That's how large our transfers are. That's actually also described in LSUSB. So I think if I extend this out and we look here at the out, it says here that our maximum packet size is 64 bytes. So that's the transfer size we're going to use. I think that we don't need to send a 64 byte thing. I think it will get padded for us, but I'm going to do it this way. So transfer buffer, and let's put some stuff in here. So let's grab this, let's put this over here. Let's send this data. So everything else is 0. When we do, wait, what did I do with the rest of it? Oh, okay, that's down there now. So we need to send this data. So byte 1 is 04. And the next one is 01, and then the next one after that is just 0, so we don't need to even really write that one, but let me get 01. So 1, 2, 3. So we only need to set 4 of these bytes, and let's pass that in, the transfer buffer. And this is it. We're going to send our first piece of data to the keyboard. It's obviously not going to do anything because we know we need to send at least 3 things to the driver. But I want to do this to show you what is going to happen. So I'm just going to send this. And you can see we got a crash. And what we got was a lib USB error IO. And it's kind of really unhelpful error actually. And I hit this the other day, and I had to do loads of Googling around, and it took me some time. But what I figured out from this is that in order for you to talk to all this stuff, you actually, and this is especially the case with human interface devices, HIDs, you need to tell the kernel that you want it to relinquish control of certain interfaces. So for instance, we're going to tell the kernel, hey, you can keep the keyboard interface 0, but we want to control interface 1. So in order for us to do that, when we set this thing up, we actually need to come in here and say device interface. Well, we need to keep track of it. I'm going to show you how this works. Device interface, and now I realize we will need to keep track of it. We can say, is there a kernel driver active? That's a method. So we can say, if there's a kernel driver active, then device interface dot how do we do this? Detach kernel driver. Yeah, so we can detach the kernel from the driver. Any book resources for learning? Yeah, take a look at the USB spec. that's the number one. Just go and look at the USB 2 specification. Like that comes with all of like the different class specifications, everything. Just read the general specification. And there is a book that I'm reading now, which is called USB Complete. It's by Jan Axelson, I think. I'm sorry if I'm getting the name wrong, but if you Google USB Complete, you'll find it. And that is a book that goes in detail about USB. And that's up to date for the latest stuff. So like USB 3, 3.1, all that stuff. Yeah, so we're going to actually detach the kernel from this driver so that we can take control of this like command endpoint. And because we're going to do that, we're actually going to want to reattach the kernel driver at the end when we're finally done with stuff. But for now, I'm going to leave that kind of thing out. Maybe it's actually worth putting in, just because. So let's have the iFace. That's Greg. Oh, we can also auto import that. That's nice. So device interface. This.iFace. And then we don't need const out there. And what I'm going to do is like we're going to have our own private variable called, I guess all of these would be private for the most part. It doesn't really matter, so let's keep it all public for now. Has detached kernel driver, and that's just going to start off as false, and this dot has detached kernel driver is going to be true. We're going to detach the kernel driver, and then later on when we'll write like a release function or a method here, and what we're going to do is if we have that detached kernel driver, then we will say this.iFace attach kernel driver. So we're going to put it down. And one more thing that we need to do is once we've detached from the kernel, we also need to claim the interface. So previously the kernel had claimed it. All we've done is tell the kernel to stop claiming it. Now we're going to claim the device, the interface. This is all stuff you can read about if you go and look at like libUSB documentation and all that kind of stuff. But yeah, so this is basically what we need to do here, and then at the end we're going to release our claim on the device. That's pretty much it. And now I think if we do this and we run this in the thing here, well, we don't see anything, and that's actually a really good sign in this case, because it just means that it didn't error out, like it actually worked. There is a caveat here that I should mention, and that is this would not work if you didn't use sudo by default, right? So if you haven't set anything up and you do this, you would have to run this with sudo, because if you're asking the kernel to literally like detach itself from something, so you need to have privileges to do that. And the reason I don't have to run as sudo is because I've set something up called a udev rule, and a udev rule is basically some configuration that you can put into the system that tells like the kernel like when certain devices are plugged in and certain devices on certain subsystems come in, including USB. You can match against that device, and you can say, I want you to allow me to have full privileges as this user, and I want to run this command when it comes on, and all of that kind of stuff. So in the end, what I plan on doing is writing a udev rule and distributing it with this package, so that you install the udev rule, and that will automatically run this driver when you plug the device in. So then it's like a true driver, right? You don't even need to worry. And as soon as you detach it, it should also automatically clean everything up. That's the idea anyway. So that's what we're going to do there. So now let's actually mess with the brightness. Let's actually go through the step of like completing one full transaction and changing the brightness level. And I think what we can actually do is put this into a method, right? I think what we should do is make a set brightness, and we'll have a level, and for now just make it a number. We know that there's actually only 4 choices, so we can restrict that further in TypeScript, but we'll just have it take a number for now. And what we're going to do here is we're going to just move this code up here. So this is going to initiate the transaction. So this is going to be basically our header, right? And then we're going to await this dot command transfer. And we need to make this an async function. Yeah, so this is now the beginnings of this. Wallowlow says sounds not very secure. You mean the udev rule? Because with a udev rule, you have to be root in order. Well, you have to be like privileged user in order to write a udev rule. So you can't. Somewhere along the way, you need to be privileged enough to tell your system that you can do this. So it is secure. Like it's no more or less secure than doing any other action as the root user and saying to your system that, hey, treat this device like this as a user, right? Because you can do this for other things. Like if you want to be able to do certain things in VirtualBox, you need to add yourself to a special group in the Linux system, and then that group has permissions to do things, right? It's the same kind of thing there. So it's not yeah. So it's not actually insecure. It's as secure as anything else, right? You have to be in control of what you're doing there. It's of course could be an attack vector. That's something different, but it's not. I wouldn't say it's inherently insecure. Okay, so now we need to kind of go back to Wireshark for a minute, because we need to kind of look at how these transactions play out. So let's start here on this one. It doesn't really matter which one we start on, but I believe 41 was the beginning of one of these transactions. So how does this work? As the host, we initiate this out, and then apparently we get some data back from the device, and we don't actually get any data back here, so that's not happening. Then we do apparently get some data back on this interface. So if we were to, we need to take a look here, and it's like this is where we apparently initiate that. This is kind of a weird thing. Obviously we don't initiate it for this part, but you can see we get some sort of response for that, and it's echoing back our stuff here. Then we're doing we're initiating this in. So we're initiating this in, which is basically saying, hey, give me some data on 82, which is our interrupt endpoint. And notice that we don't send any data here. There's no data associated with it. So what we're going to do, obviously because we're asking for data, so in this case we actually need to initiate an interrupt transfer. And notice that we need to provide a buffer here because there's data that's going to come back. Yeah, sorry, Firesnake. You're a little late in the game, but yeah, I would recommend going back and watching it from the beginning. You get to see all of the technical difficulties that happened. We need to provide this a buffer, right? We need to provide it a buffer that's data is gonna be written into. So let's make an RX buffer. And it's going to be another 64 byte buffer. So we're going to receive into our RX buffer in that case. So that's our first part done. And then we do the second part, right, which is another transfer. So what I'm going to do for this, right, is just use the same buffer and just write new data into it. So when we set the brightness level, we know that we have to send these bytes. So this is going to be our actual request. And, well, here's the nice thing, right? Byte 1 doesn't change. So we're just, actually, you know what? I'm just going to write it out because otherwise it's going to get really hacky. How many bytes are we sending here? 4, 5, 6, 7, 8, 9. We send 9 bytes. So 04, 01. Oh no, not 01. In this case, it's OB. But remember that this kind of, if we start on brightness level 0, what we send there is 0, 8, and over here, this is the byte that we would put our number 1 in. So what you'll notice is like this is 8 plus the brightness level that we're setting to, right? Because in this other case, it's 8 plus 1, which is 9. That's the brightness level. So this byte ends up being 8 plus the level of our brightness, which we really should restrict to be only those 4 values. Okay, and then we get 0, 0. So byte 2, that's like this. 4, 5, 6, 7, 8. So we get byte 0, and then 0, 6. B 0, 6, and then 0, 1, 0, 1, 0, 0, 0, 0, and then just our brightness level. So that is the thing we're doing there. So then we're going to send that, and we're going to receive again. And since we kind of don't care about the response that much, we can just like receive into the same buffer again. We probably should check out if we should look at this data. So that's our actual request. And then we have our footer, remember. And in this case, since we've written a bunch of these bytes here, I'm going to do the kind of cheap solution, which is just like reallocate a buffer. It's like horrible. Like we should actually just zero this out again, but I'm just going to reallocate a 64 byte buffer, overwrite it, and then we can write the footer, which ended with, it was the same as the header, but it basically has 2s at the end instead. So this is the footer. And if all goes well, set brightness, this should actually work. I hope this should work. What I'm going to do is I'm going to add a delay here because I want to show you this. So I want to be able to switch the screen to the other keyboard thing. So let's make a delay function. I've done this so many times now. Set number of milliseconds, and we'll set a timeout. And when the timeout is done, we'll call resolve. We want to do it after this number of milliseconds, and we need to wrap all of that in a promise, which takes a resolve and a reject. We don't need a reject, so let's just have resolve, and that's it. And then let's just say that this is parameterized on void, so we know we're not doing anything with it. So let's do this. Await driver dot set brightness, and let's first set it to 0. So we'll just turn it off, and then let's await. Let's first await a delay of a couple of seconds, so we give ourselves a little bit of time to switch, or give myself enough time to switch. 3 seconds, and then we will delay by 1 second, and then set the brightness to 1. And delay by another second, set to 2, and then by 1 more, and we'll set to the final level of 3. I really hope this works. So, TS node index, I'm then going to switch to my keyboard view, and if this works, this will be great. So, keyboard view, it turned off. Yes! I don't know how well you guys saw that on the stream. Did that? I can see that it's changing. I'm going to turn these lights off. I'm going to see if that helps with the thing. I'm going to run this again. So goes off. And then we see it scroll through those brightness levels. Awesome. So, I hope that was kind of clear. But that is it. That is like, I mean, that's obviously that's not it. That's not the end of this. But that's the process. That is what we've just done there is the process. Beginning to end. Yeah, I do understand the brightness is kind of hard to see. Like these webcams, they're not built for this. Like they're built for adapting to the light levels immediately. But what you probably saw is each time it changed the brightness, there was a kind of flicker because that happens on the keyboard. And from my end at least, I can see that it went off and then it came on a little bit and then it came on more and then it came on like to the maximum level. So it's actually working. So I think at this point I'm probably not going to do too much more because it's going to be basically more of the same process. Like we would come in here and look at these things and think, okay, like how can we set the LED mode? We need to look at like packets. Well, let's just look at like one more thing. Let's just go and look at one of these packets and see how hard it would be, because maybe we have time, and I'm already kind of over what I thought I would go for anyway. So it starts on 113 and it goes to 128. This is setting LED mode 0. Did I say 113? I actually need to go and check again now. Yeah, 113. So this is where it starts and then it ends on 128. So 113. What you guys can probably also see is that this thing starts with 0401 0001. So again, we've got the header, right? That is the header that opens up our commands, and then we see it goes through the same process again. The device echoes that back out to us. We perform another in transaction. We get some more data back from the device. It actually gives us more interesting data this time around. This one says 04, 08, 06, 01. So you can see there's a bunch of similar values going on here. Then we send a second request. And this is the request we get in that case. So let's actually copy that, because that we know at this point we have a header and a footer. So this is setting LED mode 0. We know we can ignore the first 64 bytes. And this is what we see. Alright, let's take a look at LED mode 1. You can see pretty similar packet structure, at least. It starts with a 4. We can see this 0601 thing that was going on before. Let's see what LED mode 1 looks like. So reverse engineering, blah, 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 129 to 144. So back in 129 is here. That one, of course, it's the same header, so let's just jump down to where we send the data, copy it, bring it in, and I'm going to paste it here, get rid of the first 64 bytes, and this is what we see this time around. So 0409, that's interesting, 0601, 00002. So at the very least we see that these two numbers are sequential. But yeah, we see also that this one is also changing again. So maybe that is some sort of checksummy type thing, because it's not following exactly the same pattern this time. There's like a difference of 4 values here. So not quite sure what's going on. Let's just check one more. And I'm thinking, when I played around with this before, I'm not even sure if I did something with the second value. Alright, so that would be LED mode 2, 145 to 160. 145, jump down to the second packet, grab the bytes, drop them in. So this one, 040A, and we got the 3. So this is kind of interesting now. Here we've got something changing on this one. Second byte, some of the fields. And then it would have to be like what? Like circling it around on Like some of these fields, like 6, 1, and 3. That's going to be 10. Yeah, it does look like the sum of the fields, right? Yeah. Oh, that's interesting. Yeah, maybe it is the sum of the fields indeed in this case. So we see 6, 1, and 3. So 7 plus 3 is 10. 7 plus 2 is 9. In this case, what's it going to be? Oh, so this one actually includes another thing as well. Yeah, it includes the 4 up here. That's interesting. So this is maybe not going to be quite as easy to like directly reverse engineer as the previous one. We can't just go in and set those bytes directly. We would have to reverse engineer this whole thing. But also, what you can imagine, right, is that you see everything else is in common. What we could do is we could just grab the bytes which were in particular for those things. Like, so we know that this byte changes and this byte changes, and this one is a predictable value. So really all we need to do is keep track of a table of like something like 17 of these different things. How many LED modes are there? There are 18 different LED modes, or 19 with mode 0. So we could just have an array of 19 bytes that would basically hold these kind of checksum values, or whatever it ends up being. And we know that there are also, apparently there's also a difference here. I wonder if this is encoding like the speed or direction or something like that. It could be, because these modes, they have like, some of them have speed, some of them have direction. Okay, one thing I just want to try, just while we're here, just before I stop, and however this ends up going, we'll just leave it after that. Let's call this one set LED mode. Again, just take a number for now. Same thing, transfer RX buffer, same header, same footer, and in this case, we know that like this one is like some sort of checksum, right? We know that it's changing. But what I'm going to do is I'm just going to have it start on its first value. I'm just going to say 0C. Why not? Maybe that's completely wrong, but let's just leave it like that for now. And then we'll say that mode is like this. Because I have a suspicion. Yeah, I'm interested to know what this is going to do. Like, is this going to work? Okay, so let's do it like this. Let's make a for loop. I equals 0, I is less than, and by the way, I think, just thinking about this now, LED mode 0 starts at 1, so we kind of need to add 1 to that. Yeah, we need to add 1 to the mode. Because I would like to keep the mode in like 0 index, because it's easier with enums and that kind of stuff. So, while it's less than 19, I++, and what we're going to do is we're going to do set LED mode, and we'll set it to I. And let's make these all a little bit shorter, and maybe we can just get rid of that one because we've seen the thing start. So let's just make those 500. And I'll turn my light off already so we can see it. Yeah, I'm going to run this. Maybe it's going to crash, actually. We will see. So I'm going to switch to the LED keyboard, run the driver. So first turns off, runs through the brightness levels. Okay. It doesn't appear to be changing mode. No, this looks just like it's zooming through. So I think we need to get that right. I think we need to get the like whatever's going on there with the yeah, that didn't quite work. Did I do something? I'm wondering now. I think I just didn't set the values properly. I think I needed to set different values here. So let's take a look. I'm back in the code now. Turn the lights back on for a second. I think this might just be that I've made a small mistake here and that I didn't actually come in here and change these things around. So 04C006, and then 1, and then this one has to be 4 after that. So I'm sending, apparently probably still sending brightness commands to this thing. Apparently it doesn't break if you send brightness commands that are out of range. Then 000001. Okay, let's try that. Yeah, I'm really interested to see what's going to happen with this now. I'm actually going to unplug this first. Plug this back in. Because I want it to start from trying to get it to start from like a different color mode, but doesn't seem to want to. Okay, whatever. So turn those off. Just one color, okay. Sorry about that. I'm just configuring the keyboard at this point, just trying to get it to be something. When you send footer package, I think the last 4 byte must be a 0. I think you should use libpcap in Node. It's easier to analyze the pcap file to determine the bytes in the fields. I'll take a look into it. I haven't used it before, so I don't know about that. When you send the footer package, I think the last 4 byte must be a 0. Do you mean this one? Because I think in these things, the footer is yeah, these out 3, it's usually 0402 0002. So I think that probably is okay. And I know from experience that if you get those wrong, then actually the whole device just resets. It just doesn't work properly. Alright, let's just try this out. Let's see what goes on with it. Maybe it's going to change modes. There we go. No, kind of. It did change mode. It changed mode at least once. For sure it changed mode, because this color is a different thing. RX buffer versus transfer buffer, line 131. 131, transfer buffer. Oh, you're right. You're completely right. Yeah, I wonder what effect that is going to have. I've fixed that now, actually, just off screen. Thank you for that. Let's try that again. So brightness levels. So it's changing mode somehow, but it's only staying on the same mode. So I think there's something else going on. We probably do need to get this right with the thing. But in any case, I think I'm gonna have to pick this up next time. This is definitely a really good. This is really good progress so far. I'm really happy with where this is at now. Just trying to figure out. So that is it 1, and then here at 2. Yeah, somehow this field really is determining that. See, I wonder. Yeah, so I wonder if it's really these numbers that determine it. It's kind of strange, right? They don't go in order, but yeah. And also that 4 isn't always there. So maybe LED mode 0 is special somehow? Yeah, I'm not sure. Well, in any case, yeah, this is really cool. I'm really happy with this. I'm really happy you all stayed and joined for this and checked this stuff out with me. Does anyone have any questions or anything? Like, has this all been clear? Is there things that weren't clear and that I just went through too quickly? Now is your moment to ask. So I'll open up the floor to you all. Yeah, there's a little bit of lag in the video stream, so I'm just waiting waiting for it to catch up. Let's see. Thanks, Serena. Appreciate it. Greg, yeah, I'll make sure to set up a GitHub repo for this. Yeah, I don't have one right now, of course, but I'll set one up and I'll throw it out there, and I'll make sure it's on the video link. But otherwise, I'm gonna drop it in the low-level JavaScript Discord channel. If you're not on the Discord channel, come and join the Discord channel. It's it's nice. We have a lot of nice conversations there, and there's some really there are some people who are doing some really cool stuff there as well. So you'll see a lot of interesting things. Hey, thanks, Firesnake. Thanks. I'm gonna try and say this. Huesinkan. I'm not sure where you're from, but I think I butchered your name there. Can you do per key lighting on this keyboard? I guess it would be the most interesting packets to reverse engineer. You can do per key lighting on this keyboard, indeed. And I think that's probably what we'll do in the next one. Yeah, I think we're just going to pick this up and continue with it because, yeah, I really want to cover as much of the functionality as I can in this thing. When I first set out on this, like a couple of days ago, I had the idea like, oh, this is actually something that's been annoying me for like 2 years, so I should probably do something about this. I started messing around with it already, and then I thought, I wonder if anyone else has thought of doing this. And of course, when I looked around, a couple of people have actually made like at least partial drivers, but they, as far as I can tell, the drivers that other people have written, they're not very far along. Like, they don't cover much more than switching modes and changing brightness. And like, I actually do want to cover exactly like this, like per key lighting. That's the main thing I wanted to do, actually. I wanted to set my own patterns up and play with that. But yeah, so that's something we're gonna probably get into in the next ones. And maybe also macros. And I think macros are some of the other like completely bonkers interesting things that you can do with this keyboard once you have something there for it. And then once the functionality is in place, then you have to figure out a nice API, because like most people that are going to want to like set a macro up, they're not actually going to want to write any code. They're going to want to just like write a configuration file or something like that for it. So have to think about how the driver is going to work in that way. So that's an interesting challenge as well. Yeah. Thanks, Greg. I appreciate that. All right. Well, in that case, if there aren't any more pressing questions, I want to say thanks for joining, and I hope to see you in the next ones. And okay, so just as I just seen a question come in from Stephen. Stephen says, I had a quick question about the release method, if possible, kind of minor. If I recall correctly, the code in the constructor requested the kernel give up access, and then you acquired access. But in release method, you gave access back to the kernel before you released. Does this matter, or is USB not fussed? Real stream. That's a really good question. Yeah, I mean, as you'll notice, and I should have put more logs in so that this would have been clearer. But as you will have noticed, we never actually called release. So release probably should be set up like to run on process exit. So like if any kind of signal comes in to kill the process, like we should be running the release method. And I didn't do it at the moment. But yeah, you're probably right. Probably I do actually have to call like release my claim on the driver before the kernel can reattach. I mean, in all likelihood, the kernel can probably reattach and just force this driver out. But yeah, that's a good point. So I will actually I'll go in and fix that already because I'll forget otherwise. Release. So first release the claim and then detach the kernel. The most yeah, see, the tricky thing is release has a callback. Yeah, we won't go too deep into this, but release has a callback, and if the process is exiting and we're in like a like an event handler that runs at the very end, like we can't do any asynchronous things. So like we can't wait for the release callback to come in. Use try catch finally with release. Yeah, maybe that's a good idea indeed. But the release method is asynchronous, so I'm not sure. I'm gonna have to look into how it's done. I mean, like we need to think about the process like ending in a graceful way, and if it's going to end in a non-graceful way, maybe it's not a problem. And in the end, you know, it's also fine if you just plug the keyboard out and plug it back in. You know, that's not the biggest barrier to entry in this system, so I don't mind too much if that ends up being the case, but we'll see. Blackbyte says, for my project I thought about having a text-based protocol and then spinning up a WebSocket that accepts requests. You could easily build UIs with this. Yeah, that's also a very possible way of doing it, indeed. I also thought about not doing a WebSocket, but just doing a regular socket, so like a Unix socket, which is basically the same. Like it's what WebSockets were inspired by, right? It's basically you open up a pipe, you set up a communication channel, and you can just send and receive TCP bytes through that without having the overhead of HTTP over the top or WebSocket protocol or any of that kind of stuff. You're just literally sending bytes down the tube, and you send it like, in this case, you're sending it like on your local system, and you can even set that up so the socket itself is a file, and you'll see that probably if you've used Windows and if you've used Linux and Mac and that kind of thing, you'll have seen that there are like these socket files every now and again, and like database programs will create socket files. And when you want to talk to the you know, in whatever case, the program that you're talking to or the driver or something, then you can communicate through the socket. And that's also a good way of doing it, because you just have to read and write to a socket, and you can you have to set up this connection through this socket file. That would be a fine way of doing it. I think files, like setting up a configuration file in your home directory, is also just like a classic way of configuring something. Like you just like, okay, here are all my macros. They live in a certain directory in my home user.config /.config /GMMK or something like that, and then you could have all the macro files in there, and just like when the driver boots up, it can like watch the file system, it can like load macros in the beginning, whatever, and yeah, basically send those into the keyboard. There's lots of different possibilities there, like the possibilities for API designer on this, like this fractal thing about this kind of development is like, you know, just the reverse engineering is super interesting. The USB aspect is super interesting. Like just figuring out like the architecture of that whole system and how you talk to it. And in this case, like what we have to send, all of that stuff is super interesting. Just figuring out libUSB. But then of course you have the whole interface side of it. So there's the whole thing of like, oh, here we're actually like, you know, defining how a user would use this driver. So how do we do that? And also all the udev stuff and like configuring it. So this is like, you know, the user doesn't have to be root in order to do this kind of stuff, and having it happen when you plug the keyboard in rather than having to run a program. That's also a big thing. So yeah, it's there's a lot of considerations to make. So I'm definitely gonna go further into this. Make Greg says, make a website that lets us control your keyboard. Yeah, that's super secure. Like that's we were talking about security. You know, that's how you do it. You just open it up like Twitch plays Frank's keyboard. Yeah, that would be one way. There's actually, yeah, I really like. There's so much stuff to do with USB that I'm currently sort of obsessed with, and I'm thinking about. And right now we're reverse engineering on the like on the host side, right? So we're lucky enough to be running the Linux system, and we have Wireshark, and we can sniff the USB traffic. But how do you go about reverse engineering devices? And this has nothing to do with JavaScript or TypeScript, by the way. This is just like interesting outside of all of that for me. How do you reverse engineer a device that you plug into something else, like some other kind of host that you don't control? Like, so if you have a TV, for instance, oftentimes your TV will have a USB port, and you can actually plug something into that. And in that case, how do you go about doing something like that? And well, one thing you can do is you can use a device like this. And let's see if my camera is going to focus in on this. Yeah, so this is a Great Vet 1. And it's this really cool development board, which is kind of like a well, I mean, if you've watched the Bus Pirate streams, it's kind of a lot like the Bus Pirate in that it's this multi-protocol tool for talking to different kinds of devices. But you'll notice that it has 2 USB ports on it, right? And what you can actually do with this is you can hook both of those ports into your computer, or one port into your computer and one port into something else, and you can use the device to pretend to be other USB devices. So if we were gonna so I see it's so I'm talking about the thing and I'm looking at the comments at the same time, and I see that someone says I'm out of sync since the last time you switched with the camera. Yeah, the sync seems to have been a bit of a problem in this stream. I do apologize for that. Also, someone says the GitHub link is missing in the description. Yes, the GitHub link will come eventually. I don't have a GitHub link yet. I'm going to put one in, so I'll put that in. And to get to the conclusion of that point about the Great Vet, is that's a device that you can actually script in Python to pretend to be other USB devices. So you can plug that into something you don't control, where you can't run Wireshark or something like that. And in that case, you can see how that device speaks to this device, like the thing it thinks is like the keyboard or whatever you're trying to reverse engineer. And then you can then see what is happening from that side. So that's another way of doing reverse engineering. And then you can basically do all the same kind of analysis techniques and mess around and see how to change things while writing a driver on your home computer. This is how like the Kinect was hacked back in the day, right? This is how people reverse engineered the Kinect, because the Kinect talks to the Xbox, and you don't have Wireshark on the Xbox. But what you can do is plug in, like, well, they didn't use a Great Vet, but they used something like that. So it doesn't matter, but that device is awesome. Go and read stuff about USB. Check out Ben Eater's videos about the USB protocol. He uses a fancy oscilloscope that includes a protocol analyzer and makes it really easy to decode USB traffic. Yeah, I've actually seen that video. Yeah, he got given one of those really nice Keysight oscilloscopes, I believe. I think those Keysight oscilloscopes are something like $18,000. So they're maybe I'm a little bit over the mark there, but probably not by that much. It's a pretty expensive tool, whereas the Great Vet is something like something around $100. It's a little bit less. Great Vet looks expensive. How much did you pay? Do you think a single app mega and some C would be enough to sniff USB traffic in real time? No, it wouldn't be enough for a couple of reasons. One is that USB is quite fast, so it's quite a fast protocol. So if we're talking about USB high speed, which is like the USB 2 mode, like the big USB 2 mode, that runs at 48 megabits per second, which is really fast, right? That's 48 million bits per second. That's faster than you can pick up on an Arduino or an Atmega. I mean, there are chips that can go a bit faster than that, right? But in general, you need to be able to move. You need the thing that you're sampling. You need to be able to move quite a lot faster than the thing you're sampling. So if you're running at 48 megabits per second, you need something that can run at least 3 or 4 times faster than that in order to be able to sample it and accurately get those signals. And the other thing that makes that difficult is that USB works with differential signaling. So this is getting a bit into the weeds, but you know, when we did SPI and stuff like that, what we had was a clock and a data line, and it went from 0 volts to like 3 volts to 0 volts, and that's how you indicate ones and zeros. USB doesn't do that. What USB does is it has 2 wires that are like coupled with each other, and they're like specifically like super closely length matched with each other. And those 2 wires, what they do is they send the opposite signal at all times to each other. So if you want to send a 1, like one of them will go high and one will go kind of low. And when you want to send a 0, one of them will go low and the other one will go high. And basically, in order to figure out the what the signal value is, you need to take the difference of the 2 signals. And that signaling happens at quite a low voltage, and you have to capture 2 signals at the same time. You have to synchronize them properly. It's really hard. It's actually really hard to capture USB traffic, and that is why there are like these very, very expensive machines to do it. There are also like specialized, at some point with USB, for example, like with things like keyboards, they're just interrupt endpoints, so they're just sending small amounts of data. If you have a camera, even on Ben Eater's like oscilloscope, I think you would still struggle to decode USB traffic if you were trying to watch a camera put stuff down. And in those cases, there are specialized devices which are only for USB for capturing that data. Like, even if you have super expensive logic analyzers, like I have a logic analyzer here, which isn't particularly cheap. It's a Salier logic analyzer, and even with that, you couldn't really do anything. Like, you might be able to capture a really slow USB 1 device and kind of assemble that back together, but other than that, it's quite difficult. And that's why something like the Great Fet is actually really good, because it gives you another avenue to go in there. It's not like, so it's $100, and in some ways, compared with something like an Arduino, that is quite expensive. Even compared with a Bus Pyro, which is about $20, that's quite expensive. But compared with like the tools that you need out there to like interact with USB in a physical way, like it's actually pretty cheap. Like, it's one of the cheapest things you can do to get that. So yeah, it's tricky stuff. All right. In any case, I really think I need to cut it off at this point, because it's been going for a long time. And yeah, thank you everyone for joining on this one, and thanks for sending questions in. And I hope to see you in the next one, where we're going to just do more reverse engineering and more USB hacking stuff. So yeah, I'll see you then, I guess.